So now let's talk about the effect of seepage pressure on effective stress. So when water is seeping, the effective stress at any point in a soil mass will differ from that in the static case. So seepage force causes a change in interparticle force, which will increase or decrease depending on the direction of the seepage. So downward seepage, so soil particles are more densely packed, but upward seepage, the dense soil conditions make illusions. And this ended up with these particles floating totally no effective stress at all. So let's consider the CPG force, the J, capital J, acting in the direction of flow, in this case, normal to these sections. It is the water force at X points minus out water force at Y. So this CPG force J, capital J, is water pressures, PA minus PB. It can be expressed by total head differences by considering the unit weight of water in the equations. We know about the pressure head times water unit weight times A, which is the CPG force. So this CPG force divided by volume, which is the body force in terms of force per unit volume. So these CPG pressures, small j, capital J is the CPG force, and small j is the pressure, can be expressed by hydraulic gradients and unit weight of water. I is our total head loss per water travel length, and times water unit weight, which is the CPG force. We go through the very difficult situations and then the complex equation and ended up with I gamma W, which is the CPG force. Let's keep thinking. Water flow due to hydraulic differences, which is the I. I cause water flow, right? This I times water unit weight. This is the CPG pressures. It means that if I say I gamma W CPG pressure higher than my source effective stress, then we got shoes trouble into. For examples, let's think about the upward CPG problems. Hopefully you guys understand why this condition is an upward CPG conditions, because this point total head is greater than this point. That's why water flow up. This upward CPG force is CPG pressures times volume. J is I gamma volume. I gamma W is small j times A times L, which is the volume. And then let's come up with the downward resistance. It's called soil's effective stress, soil's self-weight. So downward resistance W prime is the submerged unit weight times soils volume, comma Z minus comma W is the comma prime submerged unit weights, effective unit weights. This is the way we calculate source effective stress under our groundwater tables. This effective stress self-weight should be greater than upward seepage to secure the soil body's stabilities. If this upward seepage force increase and exceed that soil's the effective stress, no more effective stress will occur. So in order to figure out the critical states not to cause soil failures, let's compare these two seepage force and the effective stress. So we assume that these two forces should be same, then we can obtain the critical states of the conditions. So I critical is the critical states of the hydraulic loss. You call it critical hydraulic gradient. If the upward seepage force is greater than downward, it is very dangerous situation. So we need to have the some margin for critical hydraulic gradient. For example, N is 2 times or 2.5 times higher than the resistance of soils, the self-weight, so-called effective stress. This critical hydraulic gradient is the ratio of submerged unit weight to the water unit weight. It can also be expressed by specific gravity and the void ratios according to our phase relationships. How do we apply these critical hydraulic gradients and the upward seepage and the source effective stress? So in your exercise, and then go to the contents, we have coursework, FlowNet. This is a group assessment. We need to secure this dry zone. And probably we draw the flow line and then equipotential line to calculate our CPG parameters, the water pressures, then water flow, even water flow down and up. So this area is quite dangerous zone. And then we also consider the sheet piles and then water pump. Water probably comes out from the down and then we need to pump it out to secure the dry conditions. So this is the relationship between cost and then pipe penetration, and here also cost of the pump. And then you're supposed to construct flow net, 3 different pipe penetrations, and then also estimate the certain different types of our parameters from our flow net and determine the cost and the effective design, optimum design for sheet piles. So you need to write up technical report kept at 1515 pages, including abstract and introduction and main bodies, the way you find out your optimum sheet pile, and then conclusions. During this process, you should able to understand how do we draw the flow net, how can we consider upward seepage against effective stress to protect boiling conditions. What is the quick condition and boiling conditions? So simply say that upward water flow creates upward seepage pressure on the soil particles may reduce the effective stress. If high inner flow rate is achieved by increasing the hydraulic gradients, the water level differences, the seepage pressure should cancel out effective stress completely, resulting in the quick conditions, which is the boiling. This shows how the soil lost their shear strength since the interparticle stress was reduced to zero. So in a quick condition, the soil particles behave as they are suspended in water, like they are swimming. The soil particles swimming individually in muddy waters. So the soil loses its strength and behave more like a fluid than a solid. Can you imagine this water? It looks like water can support any load and then cannot. This is the quick conditions. You need to review whether this CPG upward CP cause quick condition or not in your coursework. How do we review CPG? This slide tells you about how you review the quick conditions. Water flow down, it's okay, along the flow channels by drawn by yourself, and then start to upward. And the Terjagi mentioned that half of the D is the depth of your sheet pile penetration. Here D. This area quite dangerous. So once you check on this area, whether quick conditions developed or not, it should be okay. So here, this is the way we could apply the quick condition to the flow net adjacent to the sheet pile because we expect high upward seepage pressure in the soil near downstream of the sheet pile. Water flow down and flow up. Then from D to C points, in between we have certain flow channel and equipotential line. We need to review and find out the pressure head. This is the pressure head, and then you get the average pressure head, and then you get hydraulic gradient, HM, average HM divided by travel length, D. These hydraulic gradients should be lower than critical hydraulic gradient. How do we get critical hydraulic gradients? critical hydraulic gradient, so simply submerged unit weight over water. For example, our soil is 20 kilonewton per cubic meter as a unit weight, saturated unit weight. And then mostly water unit weight is 9.81, assume 10. And then saturate minus gamma W, which is the gamma prime, which is the 10. Gamma prime is 10 over 10. Now our critical hydraulic gradient is number 1. And then now this is the 1 over this. These examples tell you about how we get the port pressures, pressure head at a certain point. I will bring certain example of the, questions from our lecture notes. Say the examples plus my additional tutorial questions. Last week, I just gave you kind of Cooper Dam the cases. We can discuss further these questions in our next week tutorial sessions.